When you develop a car, you can never look at a single component individually without taking the whole context of the car into account. In this case, there's so much architecture and packaging, as we call it in the car industry, that you don't see immediately here, but I'll explain it to you. So the W16 is a very short engine for its size, but quite wide. And the layout used to be in a way that the gearbox was in front of the engine. Now it's behind the engine. And then that gearbox was feeding the power or torque to the front axle, but also to the rear axle. So the prop shaft for the rear axle went through the engine block to the rear differential. So it was a very wicked layout. We don't actually have that connection now. The rear axle is completely separate from the front axle, and the front axle is two electric motors. There's no physical, no mechanical connection between the engine and the front wheels. But in between now we have a battery, and the gearbox moved from the front to the rear. It also enabled a different aerodynamics of the car, because now we have a narrower engine, which is also tilted in the car. It's actually not straight like here, it's at an angle, to enable a very interesting diffuser, which is double the length of a Chiron diffuser. And that's actually very beneficial, because you want downforce from underneath the car, from the body, instead of wings on top of the car, because it comes with less drag penalty. So you get more downforce for less drag. And in this case, you have super long Venturi tunnels left and right of the engine, because the engine is now narrower, and with the angle of the engine and with a lot of trickery that we did also with the rear crest structure and the suspension, which is now exposed in the airflow. So the suspension is also shaped like an airfoil, like a wing basically, because it's in the airflow. The air flows left and right next to the engine, so it was very important to keep it narrow. People sometimes forget that total aerodynamic resistance of a car is the CD times the frontal area. So it's very important to reduce the frontal area, especially for a car that goes the speeds that we do. As you know, we are about breaking speed records, and the Tourbillon is faster than the Chiron. By reducing the frontal area, by bringing the passengers closer together, by having a narrower tunnel, by having the gearbox behind the engine, it all works together as one. We wanted to show that even this naked form, without the bodywork, it's a Bugatti horseshoe, and this horseshoe does a lot of things. We have the medium temperature cooling systems here, so the air is flowing here to cool the front electric axle and the battery and the brake system, and then here comes the luggage compartment, and left and right is the cooling for the combustion engine. So when the air goes up, the car goes down. That's usually how downforce works. So in the Chiron, the air would go in here, and because of the luggage compartment, it would go underneath the car. You don't really want air to be going underneath the car from here. So instead now we have the air going up through these radiators and exit in the bonnet. The electric motors are in front of the axle, because basically the feet of the passenger and the driver of the car are coming all the way until here. So you are very close with your feet. You can't have the motors, they will be in the foot space of the passengers of the car. And then you see here is kind of a hole between the gearbox and the inverter. Why? Because this is where the steering rack goes. And then in front of the two inverters, which is also a very integrated dual inverter, so it's basically one box with two inverters for two motors. We have the luggage space, which is now completely different, and now we have a very deep but narrower luggage space. What we did with the Tourbillon was having a very narrow powertrain that's on top of that angled, so that we can channel the air left and right from the powertrain. And actually, because of that, it goes through the suspension. And you can see that here in this wing-shaped 3D printed suspension arm, and then it goes up until the end of the diffuser and then goes away, and then actually even the exhaust pipe, which is not here now, is separating the airflow from the diffuser and the turbulent air behind the car. And it's all a big interplay of different systems. On one side, the powertrain layout, which enables the whole architecture to make it work like this. But also, for example, in a normal car, what you will see here in the back now would be a big metal crash beam, like thick like this, and going from left to right all the way across the car. And we don't have that because our diffuser is actually the crash structure. So this is the diffuser cone. You can see the shape of the diffuser, but it's at the same time absorbing the crash energy. So two of these 3D printed metal structures, which have this tiny intricate little metal structures inside, which are there to absorb the energy, enable it to start with the diffuser so tall. Now when the car will be on the floor, this will be at knee height. So this is the terminal height of the diffuser. And with the diffuser you have to go in very gentle angles. You basically have to stay at around 11 degrees. And that means you can't go very aggressive, because otherwise the airflow would separate from the diffuser and the diffuser wouldn't work anymore. So if you start that high, it means the diffuser needs to be really long. And in the case of the Tourbillon, the diffuser starts in the middle of the car, basically underneath the passengers. So half of the car's length is the rear diffuser, which is perfection for an aerodynamicist. That's what they want to do. But that means then that the suspension, because of that, is in the airflow. And traditionally you wouldn't be able to make a suspension arm that's aerodynamic, because it has to be very strong to sustain the forces that it needs to do. But then comes another thing that we did for the first time in the Tourbillon, 3D printed suspension. So we see it here much more prominent in the upper wishbone, in this organic, topologically optimized shape. It basically means that software and AI is optimizing the shape of the part in order to cope with the forces that it needs to encounter during acceleration, braking, cornering, or speed bumps. And you take atom by atom away to just leave the structure where it's absolutely needed to cope with those forces, plus of course some buffer on top of that to encounter also some unpredicted situations. And that enables also the design of a wing-shaped suspension arm. You can see the difference between the upper arm and lower arm, because this one is not in the airflow, this one is. But inside of this shape, there is again microstructures that enable this kind of shape to be strong enough, but still aerodynamic. So it all works together: the narrow powertrain, the integrated crash structure, 3D printed suspension. It's not just about individual components, it's about how you bring that together to have a benefit to the overall car in terms of weight, packaging space, aerodynamic efficiency, downforce, performance, and we all bring that together in this car because we thought about all of these bold things together at the beginning of the development of the car.